Talking about the Arrhenius equation. It's page 678. Actually, that equation, instead of looking like that, this orientation or frequency factor is the letter A. So, and I had mentioned that the other day. So I just want to throw that out there in case you're kind of following along things. So remember, we said way back when that you could have two reactants going to form products, and this is the stoichiometric coefficients. We come up with the rate law expression. Rate, how fast it occurs, is going to be equal to the rate law constant times the molar concentration of all the reactants raised to the reaction order. And you can only get, we talked about how do you get M and N. But then we were taking K and we were going to break it out into this. So K is equal to K0, which is the Arrhenius constant, and that accounts for orientation, and then E raised to the negative EA over RT, where this is the activation energy and this is the orientation factor. And to me, I think of these as kind of this being the concentration element, and it all balls up into how fast a reaction will or won't occur. Okay. And then I did these, talked about exothermic reactions. How are we going to find this one right here, this activation energy? It's an energy barrier, so it's always going to be positive. And depending upon, in this case, we're going from left to right, so it's going to be actually this segment right here. That's your activation energy. Okay. All chemical reactions, whether they're exothermic or endothermic, will have an energy barrier. Energy barrier for this one is right here. So kind of hold that thought. That's your activation energy.
What if it just stayed the same? Well, like not the same, but what if it ended up as the same?
There'd still be an energy barrier. Yeah. Yeah, but yeah, it's neither endothermic or exothermic. It's a wash. Yeah. No. Oh, it would be.
You just have to go. Like,
No, kind of. Yeah. So you're saying if the energy for the reactants is the same as the energy of the products?
Yeah.
Yeah. So it would still have this.
Oh yeah.
Yeah.
But like.
Yeah, your enthalpy change would be 0.
Endo or.
Yeah. And the endo and exo actually kind of got where you just have different changes with your. Yeah. So anyway. Yep. This is another look. Actually, this is a potentially reversible reaction. So down here, we're showing it in the forward direction, where N2 and NO combine to give you N2 and NO2. So let's kind of see where our enthalpy changes here. If we're going the forward direction, this is the delta H. It's exothermic. Actually, if we're going the reverse direction, it would be endothermic. Okay, but one of the things I mentioned on the next slide is that kind of at the tippy top of our activation energy is actually what's called a transition state. Okay, so you can kind of see in this case we have all three things. It's sort of in limbo. Okay, so sort of picture that: reactants, products, transition state. All right. So transition state is something kind of in between. Sometimes it's called an activated complex. It may or may not be isolatable. Probably not. Okay. It'll be at the peak. So this is something a little bit different, and actually this is one of the reasons I brought the textbook, is because there is a mistake on this slide. Think of this as, in order for your reactants to proceed to form products, it needs the molecules, the reactants, need to have a certain amount of energy to overcome that barrier. So this is looking at, as reactants, how much energy do the reactants have? And all reactants will have kind of an assortment. This is like a belt, kind of a standard bell curve, an assortment of energies, where this is energy is increasing going here. So this is how much energy our reactants have. This high energy, and this is low energy. Well, let's just say, I'll put this whole thing up here. This right here, okay, let's say that this should say, instead of higher activation, this should say lower. And actually they corrected it in print, and this should say higher. That's on the next page. So that's on like page in my OpenStax book, page 679. But what this is saying is if your activation energy is lower, like just say that is your activation energy, EA, then you have all of these guys that can make the cut. If your activation energy is higher, and be a higher hump, then you only have these guys. And it makes sense. There's fewer of them that has that much energy, just because we kind of have this sort of distributions of energies. So this is two scenarios where these are run at two different temperatures. So if this is high energy and this is low energy, can you see where actually the black one has more volume at higher energy, and the brown one is lower temperature, lower energy. So in this case, we're going to make the brown one, the temperature is less, and the black one, the temperature is greater. So let's see if we have any more builds here. Yep. So can you see where the area, and in this case, I only have a single activation energy. This is how much energy you have to have as a minimum to proceed from reactants to products. So you can see the area on the black one is greater than the area at the lower temperature under the brown one. Makes sense. You know, warmer, you give more boost. You got more that possibly have the minimum amount of energy to proceed from reactants to go to form products. Overcome that energy barrier. We all can relate to the whole concept of an energy barrier. Okay. I have one more plot, or another plot, and actually this is, you guys are going to gather data tomorrow to do what's called an Arrhenius plot. Let me double check at the sheet you guys are going to have for your test next week. So your test next week, this sheet, let's see what is that? So down here I've got K, the rate law constant is equal to K0 E raised to the negative EA over RT. Oh, look, and I also have this. This is I'm going to show you, this is how we're going to plot it. So if you're into marking things, you could say, well, we'll wait. All right. So how can we plot something? Well, we know if you ever run into having an exponent, something raised to a power, try taking the log of both sides, and that's actually where I'm going to start. We'll go ahead, and since this is base, this is an E, base E, I'm going to use the natural log instead of log base 10. So if I take the natural log of both sides, it looks like this. And we know the law of logs say that I can do some magic here where I can actually take the log of K0 plus the log of E raised to the negative EA over RT. And it's a log. It's a log. Okay? So that's good. We end up with this. Now, I know that the natural log of E, which is the base of the natural log, raised to the negative EA over RT, that actually becomes nice, and that becomes a negative EA over RT. So I'm going to put that term right here, and I'm going to put that term over there. Okay? So, there you go. So this guy became this, and of course I just bumped that over. So that exponent of E raised to that power actually is negative EA over RT. Negative EA over R, okay, times the inverse of the absolute temperature. There we go. Now that's something we can actually sink our teeth into, and that is actually the form that you see on the cheat sheet for your test, your Unit 2 exam. So what does that look like? Y is equal to mx plus b. So we can plot along the y-axis the natural log of k, and along the x-axis the inverse of absolute temperature, and the slope will be equal to negative EA over R. ln of k, rate law constant, at different temperatures. The inverse of the absolute temperature, it's going to have a negative slope. And that slope is going to be equal to negative EA over R. And it's called an Arrhenius plot. I can never spell Arrhenius, so I just call it this. It's the A plot. That's it, man. And so tomorrow you are going to run the same, you're going to do the same chemistry as you did for last Thursday, and you're going to run it at 4 different temperatures. 4 different temperatures, and your rate log constant is going to vary. The hotter the temperature, the higher the rate log constant. So for this chemical reaction, just taking the decomposition of hydrogen iodide, okay, this data was run at 1, 2, 3, 4, 5 points, 5 different temperatures. So the rate log constant K was different at each of those temperatures. So take the natural log of K and the inverse of the temperature, absolute temperature, not bad. Then so slopes, remember, are always rise over run, delta Y over delta X. And so keep that in mind, hold that thought. Let's look at some data. So this reaction was run at several different temperatures, and the rate log constant is going to change at every temperature. So let's see what that looks like. 25, 30, 35, 40, 45. So these are the temperatures, and these are the rate log constants. So you're going to see on the next few slides how the temperature was converted to Kelvin, take the inverse of it, and we took the natural log of K and threw it up on a plot to make an Arrhenius plot. And then from the slope, we go ahead and we can knock out the activation energy, that barrier. Pretty cool. So we need to go ahead and add 273 units to our Celsius temperature, then take the inverse of that, and then take the natural log of the second column, rate log constants. Nice straight line, correlation coefficient looks great. And the slope of this, which we're going to use to complete this problem, is negative 1.08 times 10 to the 4th. And since this was a second order, I think it said, that's why the units are liters per mole per second. There we go. Okay, so this is what I said right here. Slope is equal to negative EA over R. We rearrange this, solving for activation energy. Really common to make a mistake here, but the activation energy simply then is negative slope times R. And I'm giving you R on here. Only one R, so you'll know which one to use.
Wait.
Crisscross, yeah, applesauce. Okay, so plugging in for this particular problem then, the activation energy for this reaction is negative. The slope was negative 1.1 times 10 to the 4th Kelvin. All right. And then the R we're using is 8.31 times 10 to the negative 3rd kilojoules per mole Kelvin. The units of Kelvin cancel. We're left with kilojoules per mole, which is awesome for activation energy. And our activation energy is going to be positive. 2 sig figs, because that's what I have for my slope. 2 sig figs looks like 91 kilojoules of energy per mole of reactant to decompose. No, this was to react. All right. Well, let's do another one. But in this one, we're not going to plot it. We're going to think of the Arrhenius plot, but we're just going to be given 2 data points, kind of like we did, I can't remember what problem we did recently. But you need to think of an Arrhenius plot to work this. So we're given the rate log constant at 2 temperatures. Okay, and we need to go ahead and kind of think of it in this way. Okay. So, in other words, we need to ultimately take those K's and get to the natural log of. We take the changes in those. And we need to go ahead and take those Celsius temperatures and convert them to Kelvin and take the inverse of. And then the difference in the denominator and take that ratio, and that will be our slope. We're almost done though. Then we need to remember what that slope means in order to get to activation energy. That's we're going to get it by taking it times the activation energy is equal to negative MR. Okay. So raw data looks like this. The first temperature, add 273 to get it to Kelvin. Notice we're know it to the nearest 1, so we'll put the decimal there. And the rate law constant associated with that temperature. The second temperature, we need to add 273. And again, to keep honest, we need to know that we round to the nearest ones. So that's 700 Kelvin with a decimal to show that's where the uncertainty begins with its associated rate law constant. And kind of like the other problem we worked similar to this, you can think of this a couple different ways. There's more than one way to skin this cat. I probably work it different depending upon what kind of mood I'm in. But specifically then, our delta for our particular Arrhenius plot, our delta y is the difference in the natural logs of the rate law constants, and our delta x is the difference in the inverse of the absolute temperatures. It's really easy to get your 2's and 1's mixed up, but yeah, just make sure you kind of keep your wits about you. Notice that if we take the difference of any log, whether it's the natural log or log base 10, we can go ahead and simplify it this way, where it's actually the natural log of the quotient, K2 to K1, the ratio of subtraction. It's optional. You could go ahead and make a column and you wouldn't have to do it this way. So plugging in then values that we have for K2 and K1 and T2 and T1, it looks like this. Kind of messy to me, if you ask me. But I see what I've done here is I've kind of taken it in steps, take the natural log of this ratio. In the numerator, you get 2.408. And we'll be talking more about this when we talk about pHs, actually. We're going to do more logs, base 10. But if you apply a log function to a quantity, and such as this, and we have 3 sig figs, in order to show 3 sig figs in our log number, we show it as numbers after the decimal. And then here we have the difference in the inverse of the absolute temperatures. So we're looking at 0.0011 inverse Kelvin. So notice that this is going to be units of Kelvin. Okay, so here we go. One last ratio. 2 sig figs, you're looking at a slope of negative 2.2 times 10 to the 4th Kelvin. So again, we're not quite done, we're close. So now we have slope, and to get to activation energy, we have to rearrange this. And activation energy is equal to negative slope R, where in this case, looks like this, plugging in. So a negative 2.2 times 10 to the 4th Kelvin times 0.00831 kilojoules per mole Kelvin, which by the way is the same as this, it's just not scientific notation. 2 sig figs, and dun dun dun, your activation energy is 180. And the units that didn't cancel were kilojoules and moles, so kilojoules per mole.
Could you go back 2 slides really briefly?
Sorry, this one? Wait.
The one right before.
That was 180.
Right there. I'm
This
seeing
one?
what's in yellow.
Yeah, I didn't get that.
Okay. So you got all that, right?
I didn't get the final answer.
Okay. So the way need to finish up Unit 2, obviously, for your test a week from tomorrow. So, I know, I'm going to show you. In addition to that cool thing I think you can do with Canvas. Okay, so this is what your slides look like for Unit 2. So we just finished up Part 5, and this number over here actually is how many slides there are in each part. So notice that what we're going to be faced with on Friday is I'm actually going to begin reaction mechanisms, but I can't get through reaction mechanisms. It's 52 slides. So that was fine. So we're going to start Part 6 on Friday, and then Monday I'll finish, because I hadn't entirely thought through it. So Monday I'll finish reaction mechanisms, and so it gives one more lecture day. I'll have to decide. Oh, I know, yeah, that's what I'll do. So Monday I'll finish reaction mechanisms and probably do Part 7, which is kind of optional. And then on Wednesday, assuming everybody comes, Wednesday for this unit, I actually have Sweetmarsh's review questions for kinetics. That's real helpful. So we'll actually go ahead and plan on right now doing that Wednesday. Go figure. So, and then for your test week from tomorrow.
So I guess if we have extra time today, could we do like another example question? Example question, what we just learned? Yeah. When the talk or something.
What we just learned? Like the Arrhenius equation? Okay. I can